Okay, so we're going to revisit that example from the last time. So we're doing a little bit review of what we did last class. This, we want to look at summation of 1 over n to the 1.1. Again, this one gave us a little bit trouble last time because our theorem says that it should be converging, right? Because p is greater than 1. In this particular case, p is equal to 1.1. Clearly, it is greater than 1. But we looked at the table of values, even up to 100 million. It didn't seem like it was converging to a unique number. As a matter of fact, let me change the problem a little bit here. Instead of saying using the first 5 terms, because we know even adding the first 100 million terms wasn't enough. I'm sorry. I'm going to change the problem on this one. I'm going to make it, how many terms do we need to add so that we can estimate this series with an error less than 0.001? How many terms should we add so that we can estimate this series with an error less than, so I'm going to copy the next wording, this one. How many terms should we add so that we can estimate this sum with an error less than 0.001? I mean, we saw that even 100 million wasn't enough. So what is really the correct answer here? Let's use it with our estimation theorem. Okay, let's assume that number is n, capital N. So assume the answer is n. So we want to know what n is. So by the integral estimation theorem, the integral from n to infinity, this gives us the size of the error, right? That error should be less than or equal to this integral from n to infinity of which function? 1 over what? I'm going to wait for a few moments because I know you're writing the problem as well. So when you get there, give me your suggestions, please. So when we say let n, capital N be the answer, we're saying something like this. We're saying that summation of the given series, the infinite sum, is going to be approximately the same as summation from 1 to this finite n. The only difference between them is between this infinite sum and between this finite sum is going to be 0.001. So how many terms do we need to add to get that close to the infinite sum? If you remember, we did some examples. It converged very fast. Other examples, it didn't converge very fast. So the question is, what should n be? So by the integral estimation theorem, we know the difference between the infinite sum and the finite sum should be less than what? Less than the integral from n to infinity of 1 over what? What do we normally integrate to find the error? Right, n to the 1.1, except we write it in terms of x, right? Because we're just used to integrating in terms of the x variable, so we're going to put x to the 1.1 dx. Okay, so let's integrate this now. And we want that integral to be less than 0.001. So we want that to be less than or equal to, let's say less than, they said, 1 over 1,000. Because 0.001 is 1 over 1,000. Okay. Let's do the left-hand side. What is the integral of the left-hand side? Okay, so the integral of the left-hand side is first put it up as x to the negative 1.1, right? Okay, how do you integrate x to the negative 1.1? We add 1 to the power, divide by the new power, right? So add 1 to the power, you get x to the negative 0.1, and I must divide it by negative 0.1. We're going to go from n to infinity. I will rewrite this. Anytime I say negative exponent, I know that can be written as 1 over that quantity. So this is 1 over x to the 0.1. But there was already a negative 1 over 0.1 up front, so I will also put that in there. And I will even go one step further. what is x to the 0.1? 0.1 is 1 over 10. So how could I write that as a radical? Right, 0.1 is the same as 1 over 10. So we're talking about the 10th root here, right? X to the 0.1 is the 10th root of x from n to infinity. We want this error to be less than 0.001 or 1 over 1,000. But let's first see what it is. Okay, what happens if you plug in infinity for x? It goes to 0, right? So the first term will be 0. When you look at the upper limit, we'll get 0 minus another negative will give me a positive ultimately. Now plug in the n. 10th root of n. So what I'm getting out of all of this is positive 1 over 0.1 times the 10th root of 10. Oops, x. 10th root of x. Okay. Yes. Sure. All right, x to the 0.1. 0.1 was same as 1 over 10. X to the power of 1 over 10, that represents the 10th root of x. Okay. Any other questions about what we have so far? So this is the error estimate if you were to add n terms. And we're going to set it less than what? They said, how many terms should you add so that the error is less than what? 1 over 1,000. So we want this to be less than, excuse me, when I plug in the upper limit, I got a 0, right? When I plug in the lower limit, what should I be getting when I plug in the lower limit? The lower limit is n, and it's going to be plugged in for x, right? So what will that give me? Right, 1 over the 10th root of basically n, because we plugged in the n as the lower limit, right? So this should be also n, because we're plugging the lower limit of n for x. Okay, now you want this to be less than 1 over 1,000, and basically we need to solve this inequality for n. We need to solve this for n. Okay, last time we did, let me do this. Let me collect the constants on one side, so I'm going to multiply both sides by 1,000. So now I have, and also multiply both sides by the 10th root of n. So I have 1,000 divided by 0.1 is less than 10th root of n. Now what is 1,000 over 0.1? 10,000. How would you solve for n? Again, think that there's an equal sign in the middle. If 10th root of n is equal to 10,000, how would you solve for n? Raise both sides to the power of 10. So then that means n should be greater than 10,000 to the power of 10. So this is really, really a slow converging series. So you need to add this many terms. I don't want to even want to think about what number that is. It's definitely greater than a billion or a trillion. So what did you get for that, Joshua? Right, because you can look at this base as 10 to the 4th power, right? Then you're raising it to the 10th power. So now we're saying that basically n should be greater than 10 to the 40th power, which is, you know, clearly the theorem says it converges, but when does it converge? Beyond even what scientific notebook can show us, because it converges so slowly. You would have to add up basically 10 to the 40th many terms, one more than that perhaps, to see that it's actually the error is less than 0.001. So you see how slowly convergent this is, and this is the reason why scientific notebook could not show us a clear pattern of convergence, okay? Then I asked you another question last time. I said, okay, work on this one. Summation of e to the negative n over 2. Tell me, how many terms should we add here so that the error is less than 0.001? A similar question, So let's also do this one just to get a better understanding of this concept using this integral estimation theorem. So how many terms should we add? Once again, let's assume that number of terms to be added is capital N. So then we know that the error will be less than or equal to what? If you're going to be adding n terms, or you could call k if you like. If you don't like the capital N, use k or z. Let that number represent the number of terms you're going to be adding. So what will the error be like based on the integral estimation theorem? If you like, let's go back to the actual wording of that theorem. Here it goes. Okay, so it says basically that if you're going to be estimating this infinite sum by adding only k terms, then the difference between the infinite sum and the sum using k terms, that is called the error, and that will be less than this integral from k to infinity, right? So in our case, instead of k, we're using capital N, or if you like, if you want to be saying this with the same variable, we can use k, doesn't matter. So if you want to assume that as k, so how should I set my integral now? Who can tell me? From k to infinity, what should I be integrating? Negative x over 2 dx. So the integral estimation theorem is saying that if you're going to be adding just the first k terms, for example, k could be 10. Okay, if you're going to add just the first 10 terms, the error in this estimation will be less than the integral from 10 to infinity of the function. And again, the way we looked at it last time was because basically you're adding, by adding k terms, you're adding like the areas of these rectangles. So if you're trying to estimate the error by not adding the remaining rectangles, just find the integral of everything else, and the sum of everything remaining that we didn't add should be less than that integral, okay, which from k to infinity in this case. All right, let's integrate this. What is the integral of negative e to the negative x over 2? Look at it as e to the kx. What is the integral of e to the kx in general? E to the kx divided by k, right? In this case, it's going to be e to the negative x over 2 divided by what? William, would you agree with me that it will be dividing by negative a half? Would you agree with me that we need to divide by negative a half? Because, again, e to the kx is e to the kx over k, right? So if we're integrating this, it should be e to the negative x over 2 divided by negative a half. In other words, multiply by negative 2 and go from k to infinity. Once again, I'm going to rewrite this without the negative exponent. Okay. What happens as k goes towards infinity? What happens to this quantity? It goes to 0, right? Because the bottom is going to infinity, the top is a constant, the ratio is going to 0. So that will be 0 minus. Now plug in the lower limit, the two negatives will give you a positive 2 over e to the what? K over 2, right? We're plugging k for x, so it should be e to the k over 2. Okay, now this is the error term if you're adding k terms of the series. But the question is, if this is your error term, you know, the error will be less than or equal to 2 to the 2 over e to the k over 2. And you want that to be less than 1 over 1,000, because they said, how many terms should we add? What should k be? So the error is less than 1 over 1,000. Now we need to solve this for k. And once again, I'm going to do the cross multiply. So 2,000 should be less than e to the k over 2. Now here's a challenge. We're supposed to solve this equation or inequality for k. How do I go from here? What should I be doing? The unknown is in the exponent. Yes, apply the natural log to both sides. Good suggestion. So apply ln to both sides to bring that unknown down. Ln of this equals ln of that. And now bring the k over 2 down on the right-hand side. Okay, k over 2 times ln is just going to give you k over 2. And what is ln of 2,000, by the way? What is ln of 2000? Anybody who got that? Garrett, what'd you get? 7.6. Okay. So let's finish solving this inequality. So that means k should be greater than 7.6 times 2. 15.2. Okay, now, before you run it, k should be greater than 15.2. At the same time, k is the number of terms. It should be an integer, right? So what is the first integer greater than 15.2? It is 16. So we need to go with 16 terms. K has to be 16. So if you were to add up from n equals 1 to 16 of the given series, which is e to the negative n over 2, then this will be very close to the actual infinite sum. This will be very closely approximating the infinite sum from 1 to infinity of e to the negative n over 2. And what will be the difference between them? The difference between summing infinitely many terms and summing just the first 16 terms. We know that that difference will be less than what? 0.001, less than 1 over 1,000. So it's really, this is a very fast converging series. So you can see some series, you add 16 terms, you're almost there, right? Other series, you have to add 10 to the 40 terms to get there. So it all depends on how fast the series is converging. And as we well know, they don't always have to converge. Under certain circumstances, they don't converge at all. Like if you have 1 over, for example, if you had this series, would that be convergent or divergent? That would be divergent, right? We went over this last time. This is a p series with p equals to 1/2. No matter how many terms you add, you're never going to go approach to a unique value there. It's going to get getting larger and larger without a bound as n goes from 1 to infinity. This is an example of a divergent series, right? Okay, and one last example to review last material. This is going to be about the limit comparison test. So let's go towards the limit comparison test. Okay, we've already done a few examples there. Okay, I want to do one more example. If I can find the one I want. Okay, this is going to involve a square root. So I want to go to comparison tests. There we go. Let's do this one. Determine whether the following series converge or diverge. That is the question. Determine if the given series converge or diverge. Apply any test that we've learned so far. Okay. And the given series will be summation from 1 to infinity of, I'm going to change this one. The top should be the square root of n. Oops. And the bottom should be n squared plus 1. Okay. First things first, for something like this, anytime the question says, does it converge or diverge, I always like to begin with the nth term test. Let's apply the nth term test. In other words, look at the limit of the inner portion. Does that limit go to 0? Because if not, you can quickly eliminate right away. You can say it diverges, okay? That root n over n squared plus 1, do you think that goes to 0? Right, so if we're trying to apply the nth term test by nth term test, what can we say? Look at the limit of the inner portion, the sequence portion. The degree of the bottom is higher than the degree of the top, right? The bottom has a degree 2, the top has a degree 1/2, right? So the limit is going to be 0. So what does the Nth term test tell us then? We can't use it. Basically, it's like inconclusive. In other words, remember, it was a necessary but not a sufficient condition. So yes, the limit is 0, fine, but we got to go to another test. It didn't tell us anything. Okay, to go to another test, usually when you have ratios of polynomials, in this case, root n is not a polynomial, but it's still n to a power. And specifically, when you do have ratios of polynomials, always think about the limit comparison test. That test works especially well when you have ratios of polynomials. Okay, so we're going to apply the limit comparison test. With the limit comparison test, you got to come up with a b sub n to compare it with, okay? And for that, you always look at the highest degree terms. In this case, the highest degree terms are root n on the top and n squared on the bottom. How could I simplify this? N to the 1/2 over n squared. How could this be rewritten? Exactly, because you subtract the exponents, 1/2 minus 2 is negative 3/2. It's just going to be the same as 1 over n to the 3/2. In other words, 1 over n to the 1.5, right? Okay. Do we know something about the summation of 1 over n to the 3/2? What do we know about this? The p series. This one converges, right? Exactly, because this is a p series with p greater than 1. Okay? So now, without writing any more terms, any more mathematics, we should get an idea about what the final answer will be. Then we can worry about writing it up. What do you think will be the nature of the given series? It converges. Why? Because some given series and this series that we pick for our comparison, they behave the same way, right? So we already know it's going to converge. It's just a matter of doing the formalities and writing it up. And so we're going to say, we're going to use the limit comparison test. For that test, we need to do the following. Take a limit as n goes to infinity of a sub n over b sub n. And a sub n is the given series, basically. That's what a sub n is. So that is going to be limit as n goes to infinity of, okay, a sub n is the given series. I'm writing it exactly as it is. Divided by b sub n, but that's the same thing as multiplying it by its reciprocal. Let's simplify it a little bit. Okay, what do you have on the top? N to the 3/2 multiplied by n to the 1/2. Right, add the exponents, right? N to the 1/2, add 1/2 plus 3/2. That's n to the 4/2 or n squared. On the bottom, we have n squared plus 1. And let me tell you, if you pick your b sub n the way we pick it here, by taking the ratio of the highest degree terms, you will always get a finite answer when you do the ratio of a sub n over b sub n. That's the reason is, that's exactly how we're selecting b sub n, so that when you take this ratio, these degrees on the top and the bottom will always be the same, and therefore the limit will always be finite. In this case, the limit is equal to 1. Okay, I want you to go back to the definition of the limit comparison test. What does it tell? Look at the definition of the limit comparison test right here. That ratio is 1, which is a positive constant, right? By the way, this was for positive series. A sub n is positive and b sub n is positive. So the ratio will always be positive under those circumstances. So as long as it's a finite answer, basically, we're saying that both series will act the same way. So let's put our conclusion then. So by the limit comparison test, so this is less than infinity, it's a finite constant, by limit comparison test. And remember to quote your test, whichever test it is you've used. The given series, summation root n over n squared plus 1 converges also. Because we compared it with 1 over n to the 3/2, and that one is a convergent p series. Therefore, the given series, whatever was given to us also converges by the limit comparison test. I just want to go over with this example with you so you can see that limit comparison test can also be applied in the case of square root functions or radical functions. You don't have to have just polynomial functions, basically.